Okay, so we had an Analysis 3 revision lecture from the Maths Society, and they were doing complex analysis. This is Analysis 3, near the end bit. We were doing the complex analysis tricks for solving these difficult integrals, these ones. The ones of this kind of form. So this is a real integral, but it's hard to solve using real analysis techniques, but when we use complex analysis it suddenly becomes easy to do. First of all, I want to go over what the main ideas are used to solve this problem. So the integral here, there's nothing stopping us from plotting it in the complex plane, right? We have the imaginary axis going over here and the real axis going over here. The cosine is defined for imaginary values as well, because we define cosine to be e to the something or something else. You've probably heard that before. And then we have this x squared plus 1. You can plug in i's and stuff and then go ahead and plot it, and then you get some sort of weird surface, or in fact it would be 4-dimensional, because sometimes cosine can have imaginary values as well. But you have some function, and then what you do is, because we want this integral, we would integrate it over this curve, going like that. And it would be positively oriented, it would be oriented in that way. And then if we were thinking about this as a complex thing, if we called this curve C, then we could write this in a fancy way, like C cosine Z, because it's complex, over Z squared plus I dz. But to do it this way, what we're actually doing is we're taking 2 points like this, and then we're taking the integral. So let's say this distance here is minus r to r, right? And this curve C, it depends on r. And then what we're doing, so this is the curve now. The curve is this squiggly bit, also positively oriented squiggly bit. And then we're taking the integral over the curve, and then we're sending the limit r to infinity, and then we're doing this function again. So this is going to be f of x now. I can't be asked to keep writing it. In fact, I forgot the z, didn't I? We haven't done anything yet, right? We've just added more numbers to it. But what turns out to be the useful idea, this is called the residue theorem. So what the residue theorem says is, if we have any function in the complex plane, I have some contour over it, right? Now let's suppose then we want to integrate the function f of x. So what this says is, if this function is analytic means complex differentiable, except for finitely many points inside this contour. So it can't be on the boundary of the contour. It has to be analytic on an open set containing the curve, right? It can't be just analytic here and then miss the curve, because then the curve wouldn't, you could have some weird things happening at the boundary of the curve, which might stop it from being analytic. So it should be analytic on an open set containing the curve, and within the curve you're allowed to have finitely many points that are not analytic, right? So let's just say this here and here. And so each of these points have a number assigned to them called a residue. And we'll talk about what a residue is later. Not in this video, but in another video. Okay, so in a residue. And the residue theorem says, if we integrate over this curve the function f of z dz, then it's equal to 2 pi I plus a sum of the residues. And it turns out to find these residues is actually not too hard. So these are the points where it's not analytic. So let's have a look at what this function looks like. So which points this function is not analytic at, right? It's not analytic when this denominator blows up to infinity. Everywhere else is analytic. The reason is that cosine of z you can show as analytic, and this denominator you can show as analytic, and then you can have the different sum and product rules and quotient rules, and then it says as long as the denominator is non-zero, then the quotient is analytic. So this is not analytic when z is I or minus I. So in this picture, so maybe we'll draw it again, and we have this curve CR going from minus R to R. Then here with at I and minus I, the function is not analytic and it has a residue. Now what we might want to do, we can, nothing's stopping us from making a contour going around like this. And once we do this, if I call this gamma, this C of r, this is the gamma of r, then that means that our integral C of r f of z dz plus gamma f of z dz. Well, if we put these together, what we get is the contour integral. The way we normally write this is with a little circle here, like that, to show it's a circular integral. So this is and now we have this as a circular integral. We just combine these two and we get of f of z dz. And from the residue theorem, this is equal to the sum. We can make this open set right here. It's analytic everywhere except one point inside. So one is finite. So we can use the residue theorem. That says it's 2 pi I times the residue. Now sum of the residue. Well, there's only one, so I'll just put residue. Residue at, in fact, we can put, the way they write it is res at I. So there's two things to do now. First of all, we have to find the residue at I. Second, we have to show that as r goes to infinity, this goes to 0. Then we will have that the limit as this r goes to infinity, which will just be this integral we're looking for at the start, would be equal to this, 2 pi I times the residue at I. So is that or is that not complicated as fudge? So what we will do is in the next video I will talk more about what a residue is and how you find it. And yeah, so I'll see you in the next video.